Welcome to this webinar on over-the-air testing for 5G millimeter wave ICs and modules, presented by P-Semi Corporation, a subsidiary of Murata Manufacturing Company. Hello, I am Robert Wagner, Senior Director of Product Marketing at P-Semi Corporation. In this presentation, I will cover background information on over-the-air testing, show over-the-air testing systems, and end with a summary of the material presented. Let's start with background information on over-the-air testing. First, let's take a look at 5G frequency bands. In sub-6 GHz 5G FR1 bands, the bandwidth is 600 MHz for N79 band and 900 MHz for N77 band. In comparison, millimeter wave 5G FR2 bands have defined a higher frequency and wider bandwidth up to 4 GHz with a channel bandwidth of 400 MHz. Novel devices are needed to meet the demands of millimeter wave frequencies. An example of millimeter wave technology shipping today are modules designed for IEEE 802.11ad and AY, operating at 60 GHz frequency. This slide shows the integration of 5G millimeter wave into a mobile phone. In the case of 4G and sub-6 GHz 5G, devices are solder mounted with antennas designed as a pattern inside of molded parts. RF devices and antennas are connected by PCB traces, flexible cables, connectors, and contacts. In the case of millimeter wave, Antenna Integrated Module, or AIM, is one example. AIM has millimeter wave antennas, RFICs, and a power management IC. The baseband IC integrates baseband and modem functions and is solder mounted on the PCB. AIM and baseband IC are connected via intermediate frequency signals. These IF signals go through flexible cables, connectors, and PCB traces. There are several module shapes for millimeter wave AIM. Two examples are connector type and solder mounted or SMD type. Here are some examples of millimeter wave AIM module types. For connector type AIM, there are flat shape, also called planar type, which is low profile and narrow, and L shape, also called bend type, which has a wider field of view and can radiate in multiple directions. For SMD type AIM, the module is soldered directly onto the PCB. An over-the-air measurement system must support several module types. And these measurements are needed for antenna characterization. Our next topic will be the over-the-air testing systems. This first example is an over-the-air testing system for lab evaluation of AIM. A millimeter wave RF module has an antenna, a RFIC, and other passive components. Therefore, over-the-air testing is required to measure antenna characteristics. Over-the-air tests should be conducted inside an anechoic chamber in order to avoid undesirable frequency effects and interference. For measurement accuracy, distance is required between the device under test, or DUT, and the measurement antenna. Next, let's look at different over-the-air test systems used for lab evaluation of AIM. Chamber sizes can be scaled from large chambers to small chambers, which will offer different DUT to horn antenna distance and different test objectives. In addition to the chambers shown here, which are chamber room, chamber box, small chamber, and CATR, or compact antenna test range, customized chambers can be designed in-house to measure several module types. There are many challenges to creating precise measurement systems in the millimeter wave frequency range. Key performance indicators for over-the-air test systems are accuracy, repeatability, and stability. For accuracy and repeatability, accuracy between simulation and measurement is 0.5 to 1.5 dB. Repeatability is less than 1 dB at 3 sigma. The main challenge for the test system is reducing any effects of the measurement environment. AIM size is very small, typically several millimeters to dozens of millimeters. Therefore, an antenna's radiation pattern and impedance are easily affected by a test fixture, rotator, air cooler, etc. Test system considerations include fixture materials with low permittivity and high rigidity, fixture design for lower effects to antenna characteristics, and temperature control and cooling. Back to the list of over-the-air laboratory test systems. The chamber room is the largest size and the, quote, gold standard for other test equipment. As shown in the picture, the chamber room performs 2D measurement utilizing a 3D turntable, and a rotator. Here is an equivalent isotropically radiated power, or EIRP, radiation power for a 5G millimeter wave AIM for base station, which shows a 26 gigahertz frequency measurement in this example. The results show good correlation between simulation and measurement in a chamber room. Not only bore site measurement, but also beam steering test result. The differences between simulation and measurement is 0.5 dB and 0.8 dB for cases of broadside radiation and 30-degree beam tilt. Back to the list of over-the-air laboratory test systems. The chamber box is a medium size and flexible for transmit and receive and polarization change. The chamber box performs 2D measurement with a turntable and a rotator. Here is an EIRP radiation pattern for a WiGig AIM, which shows a 60 gigahertz frequency measurement in this example. The results show good correlation between simulation and measurement in a chamber box. The difference between simulation and measurement at main beam direction is 1.3 dB, which shows good agreement of the main beam and side lobe levels, and directions in a 2D radiation pattern. Here is an example of fixture design for accuracy of radiation pattern measurement. The key item to enable a stable measurement is how to arrange the DUT with a heat sink. Several structures, such as grooves, dowel pins, and positioning holes, are used for AIM positioning accuracy. Power supply cables, IF cables, and cooling air hose are placed away from the antenna radiating direction. A small heat sink is used to prevent unintended reflection and diffraction. Low permittivity material is used for the rotator arm as not to disturb antenna radiation. High rigidity material is used for AIM positioning accuracy. Temperature control is done by heat sink and air cooling during active measurements. The small chamber is the smallest size and only has a fixed direction. The small chamber is the most flexible for transmit and receive, polarization change, receive sensitivity, throughput, surface mount type AIM, and temperature characterization. Here is an example of how an SMD type AIM can be tested without mounting the module on an evaluation board. Module mounting is accomplished through contact with conductive rubber as well as rigidity and RF transparency of DUT press plate. In a small chamber, beamforming characteristics can be evaluated by utilizing multiple measurement antennas. Here is an example of fixture design for repeatability of SMD type AIM measurement. Repeatability is achieved by position accuracy of SMD type AIM in the testing fixture. Planar alignment is achieved by using a socket with taper. DUT height is aligned to the socket height by pressing DUT into conductive rubber with a DUT press plate made of rigid material. Inside a small chamber, temperature characteristics can be evaluated using a thermal controller and thermal head. To prevent dew condensation, dry air is injected into a cover customized for air injection and constructed from low permittivity materials. Back to the list of over-the-air laboratory test systems. The Compact Antenna Test Range, or CATR, is capable of a 2D measurement utilizing a turntable and a rotator, which can be used wherever the DUT is in a quiet zone. Here are some details on CATR features and future improvement ideas. CATR anechoic chambers are commercially available that conform to 3GPP TS 38.521, FR1 and FR2. CATR can also be developed in-house with the benefit of expandability for frequency and quiet zone. CATR offers the possibility to evaluate AIM inside a communications device. A typical AIM size is dozens of millimeters, while a typical device size is dozens of centimeters. CATR future improvement ideas include more accuracy, which can be achieved based on experience with fixture design and cooling system. Support for larger devices, from a phone of approximately 10 to 15 centimeters, to a VR headset, to a base station of approximately 30 centimeters or larger. Now that we've covered lab testing, let's briefly introduce production testing. Production testing methodology is different from lab characterization. Product characterization and product design verification is done in the lab. The purpose of production testing is to test a high volume of products. Therefore, optimized test coverage for performance is required. Also, test time reduction and fastest test speed are required to minimize test cost. Murata has a proprietary test methodology that meets market requirements for high-volume production testing of millimeter wave modules. Let's wrap up with a quick summary. To evaluate the performance of a millimeter wave AIM, over-the-air testing is required. Several types of over-the-air testing systems were introduced. High accuracy and repeatability are realized through experience with fixture material selection, fixture design, and temperature control. Large chamber room and mid-sized chamber box are used for antenna radiation pattern measurement. Small chamber has good flexibility for several testing items. SMD type AIM and temperature characteristic were shown as examples of this flexibility. AIM on large-size devices can be tested by CATR, including both commercially available CATR and in-house designed CATR. In conclusion, I would like to extend a special thanks to the Murata manufacturing team that made this presentation possible. This is the end of today's webinar. Thank you for listening.